Today we stand at the brink of a technological revolution that could redefine how we approach artificial intelligence. This revolution is fueled by quantum machine learning, or QML, a field that synergizes the principles of quantum computing with the algorithms of machine learning. As we delve into this remarkable domain, it's essential to understand not just what QML is, but how it could profoundly impact the next generation of AI. Quantum computing represents a paradigm shift in our computational capabilities. Unlike classical computers which process information in binary bits of zeros and ones, quantum computers use quantum bits or qubits. These qubits harness the principles of superposition and entanglement, cornerstones of quantum mechanics, allowing quantum computers to process vast amounts of information simultaneously. This capability is not just an incremental improvement, but a monumental leap in computational power. Now imagine integrating this quantum prowess with machine learning, a field that has already demonstrated its transformative potential in AI. Machine learning algorithms, which learn from and adapt to data, have revolutionized everything from facial recognition to predicting consumer behavior. By integrating these algorithms with quantum computing, QML opens the door to solving complex problems that are currently intractable for even the most powerful supercomputers. The impact of QML could be far-reaching and unpredictable. In areas like drug discovery, financial modeling, and complex systems simulations, QML can provide solutions with unprecedented speed and accuracy. We're looking at the potential to solve optimization problems in seconds, which would take traditional computers millennia to crack. Moreover, QML is not just about speed. It's about tackling a class of problems that were previously thought unsolvable, exploring solutions in a multidimensional space that a classical computer cannot efficiently navigate. This exploration could lead to breakthroughs in understanding complex biological systems, creating new materials, and even unraveling mysteries of the universe. As we inch closer to the era of quantum supremacy, where quantum machines outperform our best classical supercomputers, the implications for AI are staggering. QML doesn't just offer a faster way to solve problems, it provides a fundamentally different way to think about and approach them. The algorithms we'll discuss today are the building blocks of this new era, an era where the boundaries of AI expand into realms we're just beginning to imagine. Quantum variational algorithms. First, we have quantum variational algorithms like QAOA and VQE. These use quantum circuits optimized by classical methods, primarily for solving optimization problems. They're adaptable for tasks like clustering in machine learning. Quantum kernel methods. Next are quantum kernel methods. They transform classical data into quantum space to compute inner products. This quantum twist enhances classical machine learning algorithms, like support vector machines, potentially offering faster feature space analysis. Quantum neural networks, QNNs. Then we have quantum neural networks, or QNNs. These networks, including quantum convolutional and recurrent neural networks, use quantum states and operations. They're promising for complex tasks like pattern recognition and data classification. Quantum annealing-based algorithms. Quantum annealing-based algorithms focus on optimization, useful in training machine learning models like Boltzmann machines. They're especially adept at solving intricate optimization problems in learning scenarios. Amplitude, amplification, and estimation algorithms. Fifth, consider amplitude amplification and estimation algorithms, like Grover's algorithm. They offer a faster way to search databases and estimate amplitudes, aiding in decision-making processes within AI applications. Quantum algorithms for linear algebra. Lastly, we have quantum algorithms for linear algebra, including the HHL algorithm. These potentially accelerate linear algebra tasks, which are foundational in many machine learning processes. Challenges and considerations. However, the field of QML faces challenges. Current quantum computers have limitations in error rates and qubit counts. Many algorithms remain theoretical, awaiting advancements in quantum technology. Conclusion. In conclusion, quantum machine learning is a burgeoning field with immense potential. It promises to transform AI problem solving, but its practical implementation is still evolving alongside quantum computing advancements.